Okay, so how do you prove that the distance between u and v is greater than or equal to 0? First of all, how do you even understand that it's greater than or equal to 0? Well, if you think back to the examples we've done, it's always been greater than or equal to 0. Why has it been greater than or equal to 0? Is it even defined? So first of all, I should have said always defined, but is it defined always? Well, let's see. Now we can go through and should go through assigning symbols to everything, but this is then going to be what? The square root of v1 minus u1 squared. I don't have room to write out anymore. Vn minus un squared. Okay? And, you just have a bunch of these things and they're all squared. So you're adding up a bunch of squares. Okay, how does that prove that it's even well-defined? Well, why would it not be well-defined? The only way it could not be well-defined is if you're taking the square root of a negative, right? So this got to be the square root of a non-negative number, at least for working in real numbers, and that's implicitly our context here. If we're working with complex numbers, with complex vector spaces, that's not a problem. And it won't be anyway because it's still going to be positive. Okay, so got to be a non-negative number. How's it a non-negative number? Well, you should be able to tell me how the sum of all these terms is not negative. Can't possibly be. Okay? And in the process, then all we have to do is observe that the square root is never negative. And that's it. We prove that it's greater than or equal to 0. Okay? Now, can you prove that distance uv is 0 if u equals v? Now, you should write that one out. You should understand well enough to write out what I'm about to write out. And hopefully you have. But here we go. Well, distance between u and u is what? The square root of u1 minus u1 squared plus up un minus un squared. And I didn't write all that out quite well enough because of room here and a bolt. But obviously all these differences are going to be 0, and that equals 0. Okay? Now, the other thing we want to prove is that I'm going to get rid of this here. Hopefully you aren't that attached to it. Yep. I want to prove that it's not so if u is not equal to v. How do you prove that? Well, and we're talking about uv, so that should be a v1. Okay? So what is it about this that's going to make the result non-zero? Okay? In other words, proving the distance of u to v is 0 if u equals v, and that's easy to prove. This takes a little more thinking. Can you come up with a reason why this isn't going to be 0 unless u equals v? Well, hopefully you've done that. If u is not equal to v, I'm going to say for some I, u sub I has to be not equal to v sub I. There has to be at least one component that's different, because if all the components are the same, then the vectors are the same, and it's certainly going to be 0. Okay? But if any of the components is different, then, well, it's going to be for some index I between 1 and n, u sub I is not going to be equal to v sub I. So v sub I minus u sub I squared is going to be greater than 0. Okay? Since v sub I minus u sub I can't be 0, if it was 0, then v sub I would be equal to u sub I. I can say not only is it not equal to 0, it's going to be greater than 0. And that's going to make the distance from u to v greater than 0. Okay. So, we've proven that the distance between u and v is 0 if and only if u equals v. Okay? It's true if u equals v, and it's not true otherwise, so it's true only if u equals v. Now you should understand the details of this and understand why this is so, and let me know if you don't.